All right, let's get into it. Today, we're going to be detectives solving a pretty fascinating superbug mystery. And our number one clue? It's a chemical that just changes color. Welcome to the case of the nitrocephalin test. Okay, so let's meet our suspects. We're looking at a bacteria called Haemophilus influenzae. Now, what you're seeing here are two different strains, and they have something in common. They're both resistant to the same antibiotic. They're both tough. But here is the central puzzle, the real head-scratcher. They might both be resistant, but they pull it off in completely different ways. So what is the difference really? And, for a doctor trying to treat an infection, how in the world can we tell them apart? Well, the answer, it turns out, is in a really clever bit of chemistry. It all boils down to a simple color clue that lets us literally see what these invisible little bugs are up to. And bam, there it is. This is it. This dramatic shift from yellow to a deep red, that's our smoking gun. That's the piece of evidence that cracks this whole case wide open. This is the nitrocephalin test in action. So what is it actually telling us? At its heart, the Nitrocefin test is a really fast, really elegant diagnostic tool. Its whole purpose, its one mission in life, is to detect a very specific microscopic weapon that some bacteria use to fight off our antibiotics. To really understand the evidence, we've got to zoom in, like way, way in, down to the molecular level. How does this color change, this chemical red flag, actually happen? So, meet our star molecule, nitrocefin. It's a compound that's naturally yellow, but I want you to look really closely at that special kind of square-shaped part of its structure. That's called a beta-lactam ring, and trust me, it is the key to this entire mystery. Now, that bacterial weapon we're hunting for, it's an enzyme called beta-lactamase. And honestly, the best way to picture it is as a tiny pair of molecular scissors. Its one and only job is to find those beta-lactam rings, like the one in our nitrocefin molecule, and just snip them open, which makes them totally useless. So you can see where this is going, right? When a bacteria is making this beta-lactamase enzyme, those little molecular scissors get right to work. They find the nitrocefin molecule and snip. They break open that all-important ring. And here's the magic. That single chemical snip is what triggers the visible change we see. As long as that ring is intact, the molecule is yellow. But the moment those scissors break it, the whole structure of the molecule changes, and suddenly it turns red. It's basically a chemical confession. You can't miss it. Okay, so now we get it. We understand the forensic science. So it's time to take this test back to our Haemophilus influenza suspects and finally unmask the culprits. This table here just lays out all the clues so neatly. You can see there are really three distinct profiles, or phenotypes, for this bacteria. We can sort them out based on the nitrocephalin test, whether the antibiotic works, and what their secret resistance trick is. Let's break them down. First step, we've got our baseline, our control group. This one is called BLNAS. This strain is totally sensitive to the antibiotic, meaning the drug works just fine. And, no surprise, when we do the nitrocephalin test, it's negative, stays yellow. So this one has no molecular scissors. Next, meet culprit number 1, BL-PAR. This strain is definitely resistant. And just look at that test. It's bright red, a positive nitrocefin test. The confession is crystal clear. This bacteria is surviving because it's producing those beta-lactamase scissors to destroy the antibiotic. And finally, we get to our most interesting suspect, culprit number 2, BLNR. Just like the last one, it's resistant to the antibiotic. But here's the plot twist. Look at its nitrocefin test. It's negative. It stays yellow. Isn't that wild? It's just as tough, but it is not using the beta-lactamase weapon at all. It has a different strategy. And this just brilliantly shows the two very different superbug strategies. You've got BLPAR, which is all about brute force, just churning out an enzyme to shred the antibiotic. But BLNAR, oh, it's stealthy. It alters a part of its own cell called PDP3. Now, this is the exact spot the antibiotic needs to attach to do its job. So by changing it, the bacteria has basically changed the locks, and the antibiotic's key just doesn't work anymore. So, case solved. We've figured out who's who and their different methods. But what are the real-world consequences here? I mean, why is knowing how they do it so important? Well, it all comes down to treatment. Knowing how a bacteria is fighting back is absolutely critical for a doctor. It lets them pick a smarter drug. They can say, oh, it's using the scissors? Okay, let's use an antibiotic that the scissors can't cut. It helps them get the right medicine to the patient fast.
3. Just think about that. This one simple test can help a doctor tell the difference between 3 totally different profiles. The sensitive one, the one with the enzyme weapon, and the one that's changed its own locks. That is a massive amount of diagnostic power from one simple color change.
And its importance goes way beyond just one patient. The Nitrocefin test is a key tool for scientists in the bigger fight against antibiotic resistance. It helps them study how these defenses spread and screen for new drugs that might be able to outsmart these bacteria. Which brings us to a final thought. We have this amazingly simple and effective test for the bacterial tricks we know about. But this is a constant evolutionary arms race. As bacteria keep evolving new and even more clever ways to resist our best drugs, you have to wonder, how will our diagnostic tests need to adapt to keep up?